Welcoming you to my talk about software-defined hardware on heterogeneous SoCs using OpenAMP. First about me, I am Peter Fecher. I finished my bachelor's degree a few months ago. I am working at PHYTEC on IoT and low-power projects. About the timeline, what we will view, I will have an introduction for you to introduce you into the topic. Then we'll talk about what is software-defined hardware in our case. I have a small live demo for you, and then we will come to a conclusion about that. But first, let's talk about modern SoCs. Most modern SoCs feature some kind of flexible interface. So, for example, NXPs FlexIO or TI's PRUs or Raspberry Pis, how is it called, PIO. These interfaces can be used to emulate almost every interface without using much main CPU power. For example, you can emulate an I2C, SPI, CAN or Modbus, or even a Motorola 68K bus. For example, for implementing something for an older project or for using it with an old monitor or something. On which SoCs we're talking about, for example, the IMX93. We have two Cortex A55 cores. We have a bunch of low power connectivity and I/O. We have a lot of other I/O, and we have here NXPs FlexIO. Also, the SoC features DMA and another N33 core. So it's about this kind of SoC class. Why do we need flexible I/O? So for agile projects. So imagine you have a customer, and the customer does not know what he wants at the end, and maybe he wants to build some sort of smart home station, and he wants to implement some interfaces but does not know what he will implement at the end or what he maybe needs to have at the end. So if you run out of interfaces, you can just add an interface using, for example, FlexIO at the end without the need of a hardware redesign. That's pretty cool because we can be more flexible in designing embedded systems. The next point is we can just add interfaces via update. So if we have, for example, the same use case, we have an agile project, we have the hardware shipped to our customer, and the customer wants to add another interface, and we prepared it so the hardware interface can be used. Then we can just add this interface, and for example, using FlexIO or the PRUs, add it via an update because it's, well, software controlled. And the last point, we can have more flexible products. So if we make a product and the customer needs many different interfaces that need to be highly configurable or need to be exchangeable, and you need a lot of it, so you can update your interfaces or configure your interfaces, but the type of the interfaces, not just for example, parameters like the baud rate or something. You can just add or change the interface. Problems is these interfaces mostly have a vendor-specific API that leads to differentiation between platforms. For example, NXP uses FlexIO, Raspberry Pi uses PIO, TI the PRUs. You don't have a unified interface for them. And maybe the vendor API is a little bit cluttered. And on top of that, some interfaces, even if they should reduce CPU power consumption, if you would do it in software have some real-time need some real-time capabilities like NXPs FlexIO. For example, this one has a one-word receive buffer, and if you use fast UART like standard 115,200 baud, you will run into timing problems when using normal Linux. You can get it with real-time Linux because a word length is 86 microseconds, and you can do it with real-time Linux, but then the kernel is copying words the whole time, and this is not good for performance. So what are we doing to fix this issue? And to make it more compatible to other platforms. So of course we can buffer the incoming data, but if the Linux is doing that, that's not good because, as I said, we need to copy the words. We need to abstract the interfaces. So if we have unified API to access all interfaces, we can use them the same way on different vendor platforms. That's really nice because we don't need to use the vendor SDK for it. The last point is we want to have a simple configuration because we're lazy, and it's nice to do something as simple as possible. So now, what is software-defined hardware in our case? It's like I said before, we want to describe which interfaces are there and configure them instead of configuring the parameters of an interface. So normally in my device tree I have a UART, I can set a baud rate, I can set stop bits, parity bits, but I want to configure which interface is on which pin, and that's without the need of having this hardware interface. How do we achieve this? The most of the infrastructure does exist already, and one major ingredient are coprocessors. So most modern SoC feature one, like the IMX93 I showed, like the, for example, TI AM64 features some, the IMX8. But how do we make use of them? Of course, as I said, we need to buffer the incoming data. Because we don't do it in Linux context, we don't have a loss of resources for Linux. And it need to communicate to Linux via some sort of interprocessor communication. And to make this a little bit simpler, we need to run some sort of RTOS on the coprocessor because we want to be modular, we want to configure it simple. So the next question we need to ask ourselves is which RTOS are we running on the coprocessor? So first idea is, well, we can do it bare metal using some vendor SDK, but like I said, that decreases modularity. We can use a vendor SDK in free RTOS like STM-Cube or MCUX on NXP, but that needs to re-implementation for each platform. And that's not what we want. So the best idea is to use Zephyr because it's very high portability, but maybe some of these flexible interfaces are missing yet. But we have the possibility to add them simply because it's open source. So why should we use Zephyr instead of implementing something our own? Well, it's a modern, advanced, lightweight RTOS. It's maintained. It has a great portability, like I said. It uses device tree and kconfig, which is similar to the Linux kernel, and it has OpenAMP support. So short excursion to OpenAMP. Who of you knows what OpenAMP does? Okay, some people, I think it's like the half of the room. So OpenAMP is a framework that allows us to manage heterogeneous multiprocessor systems. Like in our case, we have a A55 core and a M33 core, and we want to manage them. We want to exchange data. So OpenAMP consists of two major parts. One of them, it's remote proc. It's for lifecycle management of the coprocessor and for resource management. So it starts the coprocessor, it stops it, it reserves memory in Linux, all that stuff. It suspends the coprocessor, of course. It loads the firmware, and the other half is is RPMSG, remote processor messaging. It's a bidirectional communications interface for coprocessors. With this knowledge, we can take a look on how our system for software-defined hardware shall look. And I have this little graphic. So starting at the applications processor, we have Linux. And we have the real-time processor, or the M-core or coprocessor. And like I said, we have some sort of communication between them. And in this example, we're using FlexIO with the coprocessor application that is controlling it. Controlling the FlexIO peripheral, buffering data and giving that data to Linux. In this case, a Linux kernel module, which is then creating the devices in user space we can use like a standard Linux device. So I have like a /dev/tty for my UART in this case. So to abstract it further, we can divide the system in two sides because we need to have two softwares, two applications. We have the Zephyr side and the Linux side, and the Zephyr side needs to handle all interfaces. So we implement each interface in an own module. This allows us to run every module for an interface in a separate thread. So if you're configuring like two UARTs, two UART modules will start it for the peripheral and separate threads. So we can take everything apart and nothing blocks each other. And each module opens then a RPMSG endpoint to Linux. So like one UART module is started, it opens an UART1 endpoint, and if another UART module is started, it will open a second, and the kernel module will then need to be started, but that is later. And that leads to great modularity. So because we have the modules, we can start the modules independently and can use them independently, and nothing is interconnected between them. On the Linux side, each interface is implemented as its own kernel module. So like I said, it shall present devices in userland, and for every RPMSG endpoint, a instance of the fitting kernel module is created. So if I have UART1 and UART2 as an endpoint, two UART kernel modules are created, which results in two UART device files being created. So I have then, for example, /dev/tty sth1 and 2. And basically, we're building a bridge between the coprocessor and the userland. And our goal is to have this as with a single point of configuration if we have the system working for once. So let's take a look on how we can configure it. we just need to configure it on the Zephyr side, because as I said, Linux will instantiate the kernel modules for every interface Zephyr or every Zephyr module that creates an endpoint. So we can configure it via a single device tree file. This could look like that. So we have our node with software-defined hardware devices. It has a compatible, and inside of there we have our devices that we want to create. And this device, this node is just referencing a real UART device, or our FlexIO UART device, or maybe our I2C device. Yeah, so we need to abstract this a little bit of what is like the minimum structure of one Zephyr module, and after that I will show you the minimal structure of a Linux kernel module and what it needs to do. So the first thing a module needs to have is an entry point, so we can start it, of course, as a new thread. We need to have some sort of init function that sets up the device and the RPMSG endpoint, and we need to have, of course, a RPMSG callback and a work consumer, because the data needs to be go in and out. And for some interfaces, we maybe need a callback and a consumer if we want to use it asynchronously or not. And of course, we need instance-based state data, because we have multiple instances of the same module working in one memory space. For the Linux kernel module, so we need entry points if we want to do a RPMSG driver. We need to have a probe, a callback, and a remove, like in most kernel modules. And we need the endpoint name as ID, so the kernel knows when to instantiate this kernel module. And this leads to this kernel module then sets up the device and the callbacks in userland to create a device, so the user can use it. And of course, we need some instance-based state data. And let's have a further look on how Linux communicates with Zephyr. So we have Zephyr here, and we have a thread here, we have the Linux kernel and our module. So after starting the coprocessor, what happens is that the Zephyr program is started. Zephyr creates an RPMSG channel. On this channel, that then starts the device threads. And on this channel we created earlier, the new endpoints are created. So, for example, we have one UART and the endpoint is created. So Linux starts the kernel module. The kernel module creates the TTY device, and then we can communicate over this endpoint back and forth. And if we stop Zephyr or shut down Linux, the endpoints shall be closed. How are interfaces displayed in Linux? So I made a little table. So at the moment, just UART and I2C is working, but everything can be more or less added simply. Only a Linux kernel module and a Zephyr module need to be added. So UART is at the moment in /dev/tty SDH for software-defined hardware, starting at 0, and an I2C bus is created like a normal named I2C bus. So now I have a small live demo for you. I have a Fight board Pollux with an IMX8M Plus for you, and I will start it. there. So I have configured for 2. Is that readable? I need to look how this works. Normally I'm using Linux, but I wanted to have PowerPoint. So is this better? Not really, or is can make it a little bit bigger. So first we need to insert our kernel modules. We have our I2C kernel module, and we have our TTY kernel module. So they're inserted. They should detect if there's a new RPMSG endpoint. So to start the coprocessor, we use remote proc. For that, we need to echo the firmware file into the driver. Sysclass remote proc 0 and firmware. So after that we can start the coprocessor. So we can see something's happening. We can see here that Zephyr has started. And we can see here that something's happened. We can take a look on it. So we can see the RPMSG host is online. That's good. We see that there's a channel created, SDH TTY, and we can see there's another channel created, SDH TTY. And we can see there's a RPMSG I2C channel created. And we can see here an I2C adapters registered. And if we take a look at the TTYs, we can see we have /dev/TTY, SDH 0 and 1. And we can now just use, for example, microcom to write on that. And we can see that in this shell here, the input is arriving. It's there are some debug messages, but you can see there's some data there. And of course, we can also write to the I2C. I need to find the command. So if I send this, an LED on the Pollux board should light up in I think magenta. So I'm holding it so you can see. And does it? Oh. So it sent it. It sent the command via the coprocessor to the I2C. Yeah, that's the demo. Let's get back to the presentation. So let's come to a conclusion. First of all, it's just a prototype for now. It's not something that's finished in any way. I just wanted to have a proof of concept that it works. Coming to our pros and cons. So we have made a system we can have like as many interfaces as we want. We can use the coprocessor to interact with the flexible interfaces, but we also could bit bang interfaces, and we have them in Linux like their normal interfaces. That means we can do any interface that we want. So we can even implement our own interface as long as the coprocessor is fast enough to bit bang it. We have a single point of configuration as soon as OpenAMP works and we install the Linux kernel modules. And we have a high level of abstraction with Zephyr. So we can easily port this application to any other SoC that is featuring some shared memory, a coprocessor, and the BSP also needs to support OpenAMP, of course. But if that's there, the application should run without major reconfiguring. Like I said, every interface can be implemented if the coprocessor is fast enough. And if we have enough memory to buffer it, of course, we can't just take gigabits of data and buffer it in the RAM. Coming to cons. So it's more complicated, of course. If I just use the interface in Linux, it's easy. I have it in Linux, it works. And now I need to have another application stack and need to start on the coprocessor and maybe need to compile another program. Sometimes it can be nasty. It's possibly slower than accessing hardware directly in Linux because you need to copy data at one point. And if you use multiple interfaces on the coprocessor, maybe you can't go full speed because, well, it's just an M33 running at around 100 megahertz. And if you use 4 UARTs, for example, it's maybe too slow to go at really high speeds. Zephyr support for flexible interfaces lags a little bit behind. So the IMX8 does not have FlexIO, so I used the normal standard UART interface here because Zephyr is not running, it's not working with the FlexIO on the IMX93 for now. I initially wanted to do it on the IMX93, but I didn't got it to work. And it cannot replace an FPGA solution where you really can do everything you want. And that's for pros and cons. Now we will take a look on how the prototype can evolve. So the coprocessor is of course able to do more than just bridging data. It's, well, a processor and it can pre-process data if you want that. For example, you can, well, listen to a UART or a CAN and do something on a keyword or a special command. So for example, if you have Linux sleeping, you can wake it up on an event and pre-process simpler data and keep Linux sleeping for low power applications or something. The prototype is open source and, well, new ideas can easily be added, so everyone can just change what happens. On the Linux side, how can the prototype evolve? So at the moment, as I said, any interface is bridged via its single kernel module. But I think there is a possibility to make it better because OpenAMP can utilize VirtIO virtual devices. And I didn't understand the documentation completely for that, to be honest. But I think it can be done, so OpenAMP just creates a virtual VirtIO device that then can be used in Linux instead of doing your own stuff with a kernel module. And for those who don't know VirtIO, it's thought for hypervisors and virtualization, so you can do bridges between your host and guest OS. And the coprocessor is basically a guest in our system that we want to bridge data to and from. And I think this could make the system faster and simpler because we don't need to implement our own kernel module for bridging. Instead, we use some working stuff. That does not mean that what I did does not work. I think if we use a standard, it's better. So coming to lessons learned, what have I learned along this way doing the software-defined hardware? Debugging on heterogeneous architectures can be really difficult because you can't just connect your JTAG and just debug the M core, because Linux need to know, is the M core started, is it halted, is it suspended, and it's horrible sometimes because they're interacting and they're going into timeouts if you don't continue fast enough. So you can run in really big problems with debugging. Configuring kernel and device tree for OpenAMP can be a little bit difficult. I had problems with that. Jonas helped me, so my colleague Jonas helped me with that, and I'm really happy about that. I don't know if the documentation is better now, but as I was doing this, the documentation for RPMSG and OpenAMP with device tree and config was a little bit messy. And trial and error can be really tricky too, because, well, the lack of debugging possibilities, and often you don't know what to change to make it working, or what's the problem. So the coprocessor just hangs, or Linux just panics, and you don't know what's happening, and that's not nice. But if OpenAMP works, it works like a charm. It just works. You can create your RPMSD channels like you want, and it just works on both sides in kernel and user space. Yeah, so that's it from my side. Thanks for listening. And do you have any questions? Yeah, I will give you the mic quick.
Thank you for your talk. Have you considered having your kernel module sort of raise a UDEV event so that you don't have to insert both your UART and your I2C, I2C modules right at the start, and they can be dynamically loaded?
I did not consider this, but actually I'm not an expert on writing Linux kernel modules, so I'm relatively new to that topic, but it's a good idea, I think. I will have a look into it.
An event that you can trigger on that tells you, hey, the interface is here now. It might be.
Yeah, that's a good idea, but I also can just compile the kernel module into my root file system, and the kernel automatically loads it. If this RPMSG endpoint you write into your kernel module ID is there, the kernel module will be loaded and activated. So it does. Yeah, you need to inject it, but it just does things when the RPMSG endpoint is there. More questions? Yeah?
Did you measure throughput of the IPC channel?
Sorry?
Throughput of IPC channel between big and little processors. Memory copy throughput.
Huh? Can you repeat that? Or I give you the mic. Maybe it's.
Sorry for my short English. Did you measure the throughput between big and little processors? Memory copy.
The latency.
Yeah. No, throughput.
Oh, the throughput. Yeah, I measured it once. But as I measured it, I had some problems with actually sending bytes from the coprocessor to the main processor. Some buffer was, if some buffer was full, somehow OpenAMP did not free it after reading it, and I don't know the problem. But from Linux to the coprocessor, it was. I tested it with 115,200 baud, 2 interfaces in parallel. This did work, but the other directions has some problems, and I didn't figure it out yet why. Yeah.
You have a link to the code, or
Yeah, this right.
Yeah, there. You can view it. There's everything there. There's the kernel module and the Zephyr code.
so far it's like you don't start with anything, right? It has its own module. Like I mean, you might have used MFD, multi-functional devices for.
Mhm.
And what I'm trying to say is that once you do this, it's good to send our RFC to mailing lists, because you get ideas on how to do it, and you don't start on the wrong path.
Yeah.
With this one.
Yeah.
Because I've seen some patches from NXP for a similar problem right now. I think.
Yeah, I've talked to NXP at their booth, and they told me about something similar, and I didn't knew it before.
Yeah, because if you send patches already, you find people with the same problem, and you work together instead of being separate stuff and duplicating.
Yeah, yeah.
It's a really interesting project.
Thanks. But yeah, I'll need to get deeper into that, to connecting with other people of the community, and yeah. So, any more questions?
This is more of an open question to the room. I also don't have a lot of experience with OpenAMP, but would it be possible to somehow attach like a debugger through OpenAMP to the other core to step it from the Linux side instead of using an external debugger?
Zephyr doesn't support it. It supports it with x86, so you can use user mode debugging, like the same over UART or Ethernet. So you could potentially also do it over RTOS if you want.
Also, Texas Instruments had done something in this direction. They've done a buffer for log messages and tracing.
Yeah.
Exactly the same. So in theory it's possible, but you need to implement something on the Zephyr side to interpret the commands, the GDB commands, and send you back the answer. I also had this problem of it, because when you attach a GPAG to the M4, you get timeouts, and you need to trim everything on the other side. It's hard, but it can be done.
Yeah.
I think it's the only thing that you have at some point. You have the debugger, and you need to work with it.
Yeah, of course.
And then once you have the console, the serial console, it gets easier, because you can put some codes there. And with the usual stuff, what we do is we use the shared memory area, and we write things there and read them on the other side. If you don't have the serial console yet, right?
Yeah. So serial works on my board, but it's similar to what Texas Instruments does with their stack with their trace buffer, isn't it?
Demo works on 93 or on IMX8.
This was an IMX8M+. I didn't got it to work on the IMX93 yet. There were some Zephyr drivers missing, especially the mailbox driver was missing. And without the mailbox, it doesn't work. So I guess that's it.
Thank you.